Hey everyone, and welcome. So today we are going to tackle one of the biggest, most misunderstood buzzwords out there, the cloud. We're going to peel back all the layers, from the big picture ideas right down to the nitty-gritty code that actually makes it all work.
But, let's just start with the most obvious question. We all say the cloud. We know it's not actually up in the sky. So where is it? Like physically, where does it live? And what is it really? That's the puzzle we're going to solve today.
Okay, so to get to the bottom of that, we kind of have to start with the official definition. But don't worry, what's really important is the big idea behind it, because honestly, it's an idea that totally flipped how we think about computers on its head.
So here you go, the official definition from NIST. And yeah, I know, it looks a little academic, but let's just zero in on two parts: on-demand access and a shared pool. The key thing to get is that the cloud isn't really a place so much as it is a model for how we get stuff. It's just like your electricity, right? You don't own a power plant, you just flip a switch, get power on demand from a shared grid, and you pay for what you use. The cloud is exactly that, but for computing power instead of electricity.
So what makes this different from, just having a server closet down the hall? Well, it boils down to these 5 key things. First up, on-demand self-service. You can literally spin up a server with your credit card. Right now, no phone calls needed. Then there's broad network access, which just means you can get to it from anywhere, your phone, your laptop, you name it. Resource pooling, that's our power plant idea again. The cloud company pools all its computers to serve tons of people. Rapid elasticity. Okay, this one's a game changer. You can instantly scale up for a huge event, like Black Friday, and then scale right back down the next day. And the last one, measured service, is the real magic ingredient. You pay only for what you actually use. It completely changes the economics.
Yeah? And that measured service thing, it led to this huge shift in how businesses spend money. The old way was all about CapEx, capital expenditure. You had to spend a ton of money up front to buy servers and build data centers, hoping you bought enough. The cloud flips that to OpEx, or operational expenditure. It's all pay as you go. So you stop buying the whole power plant and just start paying the monthly utility bill. It's a massive difference. Okay, so it's super important to remember that the cloud isn't just one single thing. It's more like a menu at a restaurant. You can order different kinds of service depending on exactly what you need. So let's take a look at the 3 main options on that menu.
And a great way to think about this is with a restaurant analogy. At the very bottom, you've got infrastructure as a service, or IaaS. This is like renting an empty restaurant kitchen. You get the ovens, the plumbing, the space, but you have to bring all your own food and recipes and do all the cooking. Next up is platform as a service, or PaaS. This is kind of like getting a meal kit box delivered. They give you the pre-portioned ingredients and the recipe card, but you still have to do the actual cooking yourself. And at the very top, we have software as a service, or SaaS. This is just dining out. You show up, order your food, and the restaurant takes care of absolutely everything else.
And the funny thing is, you're using all 3 of these every single day, maybe without even thinking about it. SaaS is the easy one. That's your Gmail, your Netflix. It's a finished product you just use. PaaS is more for developers. It's a platform they use to build applications without having to manage the servers underneath. And IaaS, things like Amazon EC2, are the raw building blocks. They're the virtual servers that everything else is built on top of.
But wait a second, how does this even work? How can one giant company give millions of people exactly the computing resources they need exactly when they need them? Well, it all comes down to a really clever technological magic trick. And that magic trick has a name: virtualization. This is, without a doubt, the core technology that makes the cloud possible. The whole idea is to break the connection between your software, like your operating system and your apps, and the physical piece of metal it's running on. And when you do that, you can take one giant, powerful server and slice it up so it acts like a whole bunch of smaller, totally independent servers. So this power to carve up a single physical machine into dozens of virtual ones, it's all thanks to one very special piece of software. And that's the hypervisor. You can think of it as the magician behind the curtain. It's this super thin software layer that sits right on top of the bare metal hardware. Its entire job is to create and manage all those virtual machines. It's like a traffic cop, directing the physical resources, telling each virtual machine exactly how much CPU power and memory it gets to use. This is the technology that makes that whole resource pooling idea actually work. Okay, so we've got the business model, we've got the software magic, but we still haven't really answered our first question. Where does all this stuff actually live? Well, let's finally pull back the curtain. The cloud isn't in the sky, it lives right here on the ground. It lives in these massive, usually windowless buildings called data centers. And inside, it's just rows and rows and rows of server racks, blinking lights, network switches, all tied together with miles of fiber optic cable. And keeping all that from melting, it requires some seriously complex power and cooling systems. This is the physical reality of that shared pool of resources we were talking about. Now, as you can imagine, running one of these buildings takes a mind-boggling amount of electricity. So for the big cloud companies, efficiency is everything. And the one number they are absolutely obsessed with is called PUE, or Power Usage Effectiveness. It's a really simple idea. It just measures how much of the electricity coming into the building is actually used to power the computers versus how much is wasted on things like the cooling systems.
And this really shows you what that means. A PUE of 2.0 is pretty bad. It means for every watt you use for computing, you're wasting another whole watt just on overhead, like cooling. A perfect score would be 1.0. The big cloud providers have gotten so good at this, they've engineered their data centers to run at a PUE of around 1.1. That is an insane level of efficiency that most companies could only dream of. And that efficiency, it saves them money, which in the end saves us money.
All right, so we've built this incredibly efficient worldwide computer. So what do we do with it? Well, one of the biggest problems it was designed to solve is how to handle the absolute tsunami of data our modern world is creating every single second. To deal with that data tsunami, you need the right tools. And the cloud gives you a few different kinds of storage. First, you've got block storage. Think of this as just a raw, super fast hard drive that you attach to your virtual server. Then there's file storage, which is exactly what it sounds like, the folders and file system we're all used to, like a shared network drive. But for really, really big data, the game changer is object storage. Instead of files and folders, you have these self-contained objects. Think of every photo, every video, every log file as its own little package with a unique ticket number. It's more like a giant, infinitely scalable valet parking system for data. And that's what lets it grow to unbelievable sizes. And the whole point is, you have to pick the right tool for the job. Block storage is perfect for something like a high-speed database. File storage is great for your company's shared documents. But when you're dealing with petabytes of data for big data analysis, or when you're streaming a Netflix movie, object storage is really the only thing that's built to handle that kind of mind-boggling scale. Okay, so you've got all your data sitting in object storage. Now what? How on earth do you analyze it? You can't just load a petabyte of data onto a single laptop, right? The answer is a classic divide and conquer strategy. It's called data parallel analytics. You take your one massive problem, you break it up into thousands of little bite-sized pieces, and you get thousands of servers to work on all those little pieces at the exact same time. The classic example of this is a framework called MapReduce. Imagine your job is to count every single word in the entire Library of Congress. Impossible, right? Not with MapReduce. The map step is where you give one book to 1,000 different people and tell them just count the words in your book. Easy enough. Then comes the shuffle and sort step. This is where everyone who counts for the word the puts their results in one pile, everyone with and puts their results in another pile, and so on. And finally, the reduce step. You just have one person add up the numbers in each pile to get the grand total. See? You just turned an impossible job into thousands of really simple ones. And this entire divide and conquer approach is built on one simple, beautiful idea. Move the code to the data, not the data to the code. Just think about it for a second. Trying to move a petabyte of data across a network is like trying to ship every book in a library across the country. It would be ridiculously slow and expensive. But moving a little piece of code, that's like emailing your librarian a simple set of instructions. It's tiny and instantaneous. So instead of bringing the mountain to Mohammed, you bring Mohammed to the mountain. That is the secret sauce for high-performance computing at a massive scale. So when you put it all together, the pay-as-you-go economics, the virtualization magic trick, those hyper-efficient data centers, and these powerful ways of processing data, you start to see that the cloud isn't just someone else's computer. It's something much bigger. It's like a single global computer built out of millions of interconnected machines. And that leaves us with one final question to think about. What's the next impossible problem that this global computer is going to solve?